I'm Vaidehi. I'm so excited because today I get to talk to you about implementing depth-first search. There are three commonly used strategies when it comes to implementing depth-first search, and we refer to them as pre-order, in-order, and post-order. In pre-order search, we're going to traverse through the binary tree by reading the data of the root node and then looking at its left and right references if the node has any. In contrast, with in-order traversal, we read the left reference, then the data of the node, and then the right reference, if they exist. Finally, in post-order traversal, we first read the left reference, then the right reference, and end by reading the root node or the node in the context data. We can implement all three of these strategies using something called recursion. So what is recursion? Well, recursion is a concept that's used in lots of different contexts in computing, not just in computer science, but also in just programming as a whole. Recursion is the idea where you can call a function from within itself. It's particularly useful when you find yourself repeating the same steps again and again. For example, if you have a function and you need to call that function from the context of itself, you can use recursion to call the function from within itself. And that is what effectively allows you to repeat the same actions again and again. And we can actually use recursion when we go about implementing DFS. But why is this? Well, if you think about each of the strategies, they're all slightly different because they're all either reading the data of the root node or the left and right reference in some order. But you're usually going to only use one strategy when you implement depth-first search. So for example, if you're using pre-order search, no matter what, you're always going to read the data first, and then the left reference, and then the right reference. Because you're taking the same steps again and again for each node in the tree, you effectively need to repeat yourself for every single node that you encounter. This lends itself really well to using recursion. We can use recursion when we implement any of these three depth-first search strategies. Eventually, we're going to need to check and visit every single node in the tree data structure. We know that the amount of time that it'll take to run depth-first search is dependent directly on how many nodes we have to check. This brings us to the time complexity of this algorithm. Depth-first search will at least run in O of n time. When we say O of n, we're actually talking about the big O time complexity of this algorithm. O of n simply means that the amount of time that it takes to run depth-first search is linearly proportional to the number of nodes in the tree. So how do we go about implementing this in code format? So let's just start by looking at something simple. Let's look at how we would code a node. Here we have a single node that I've called node 1. Recall that a node only has 3 little bits of data associated with it. First, we have the data itself, and it will have a reference to a left child and a right child. We can see here that the data is just represented in this hash or dictionary or object, depending on the language that you're working with. Of course, we need to have a reference to the left child and the right child. However, the left child or the right child could be empty. If both of these references are empty, then we know we've reached a leaf node. Remember that a leaf node has no children. So let's take it a step further. We know how we might code a node, but how would we code a pre-order search function, one of the strategies that we can use for DFS? Well, we know that the pre-order search function is going to have to start by taking in some sort of node. Remember that we're eventually going to try to use this function to work for all nodes in the tree, so we need to keep that in mind. But we'll get to the recursion part in a second. The first thing that we need to do when implementing a pre-order search function is make sure that we pass in the node that we're trying to check. This is especially important because we're going to start with the root node, so that'll be the first node we pass. But remember that we want to be able to make this function work for all nodes in the tree. We also need to check whether the node actually exists or not. If we're passing a reference to a node into this function, but the node doesn't exist, we actually know that the previous node was a leaf node. And we know that this node has nothing to check. So we want to short circuit and exit out of the function immediately. Checking that the node exists is important for establishing the base case of this function. The base case is important for a recursive function because that's how you avoid the function going on and on forever and causing a stack overflow. So this is our base case. Because this is a pre-order search function, the next thing we'll want to do is print out the data and read the data of the node we just took in. Remember that pre-order search is DLR. So we'll read the data of the node we're looking at. Now we need to do the L and R bit of the DLR strategy. This is where the recursion comes in. We actually know that we want to do the exact same steps for the left reference and the right reference if they exist. We already have a function that does exactly what we want. So we can actually call that same function from within itself. Here, we're calling the pre-order search function recursively, and we're going to pass in the left reference and the right reference. This is the recursive aspect of implementing DFS. Because we're going to take the same steps in the same order for every node in the tree, we can use the same function and call it from within itself. This makes implementing DFS pretty easy once you have one function that does all the things it needs to do. So we've talked about time complexity, but what about space complexity? Well, recursion plays an important role here too. The first time that we call the pre-order search function with our first node, what we're actually doing is allocating a stack frame and adding it to our call stack. Remember, if we're using recursion, we're calling a function from within itself. So when we call the same pre-order search function for the left child and then again for the right child node, each time we're adding another stack frame to the call stack. As we add stack frames to our call stack, we'll notice that this is corresponding directly to the number of times we recursively call the pre-order search function. This means that as we work our way down the tree data structure until we hit a leaf node, each time that we call the pre-order search function recursively on a node, we're adding a stack frame to the call stack. And we're going to continue doing that until we hit the leaf node. Finally, when we add the leaf node to the top of the stack, we can finish running the DFS for this path, and we'll pop all of them off the stack as we work our way back up. This only happens at the leaf node because there are no other nodes to check. The call stack that we're seeing right here is actually a throwback to the stack data structure, which operates on the LIFO principle, which is last in, first out. To learn more about the stack data structure, check out my episode on exactly that in Season 1. So this means that the number of stack frames we add to our call stack corresponds to how many nodes we check in a path. When we hit the leaf node, we finally have added all the stack frames to our stack, and we can start popping them off. So what does this mean in the context of space complexity? Well, the call stack is going to grow in height until we hit a leaf node. That means that the amount of memory, the amount of space that the call stack needs has to do with how many function calls we make. And that has to do with how long our path is until we hit the leaf node. The technical term for talking about the space complexity is O of H, where H is the height of the tree. Recall that height has to do with the longest path or the path to the furthest leaf. In this case, we're talking about the height of the tree itself. So the amount of memory required to implement DFS recursively has to do with the height of the tree, where O of H corresponds to the space complexity, and H is the height of the tree. To learn more about implementing depth-first search, head over to dev.to, create an account, and follow me at Vaidehi Joshi. You can also stay up to date on all my upcoming videos. Thanks for watching.
Thanks to Heroku for sponsoring BaseCS. I'm Ben, one of the founders of Dev, and I want to give a shout out to Heroku, the platform that's allowed us to scale from 0 to millions of monthly visitors since we started this venture a few years ago. We rely on Heroku's managed Postgres alongside the rest of their infrastructure to ensure reliability and flexibility as we scale. If you're looking to scale a complex web app without all the chaos, please check out Heroku. Thanks a lot.